Okay. Thank you very much for the nice introduction. I guess the slides should be on. Almost. Okay. As you can see from the title, I want to talk about the automation of quantum machine learning, and I will first talk a little bit about what the project AutoQML is about and the framework, and then Horst will tell you about a specific use case and an application of the framework. So I already mentioned AutoQML is a project, but we made a critical design flaw right from the beginning because it's also the name of the framework. So I will try to keep these two things as separate as I can and not confuse you. What was the original motivation for doing this project? It's basically quantum machine learning is complicated, which does not mean you have to be super clever to do it, but you have to be at least knowledgeable in 2 domains. And I guess for machine learning, the scarcity in people that know about it is not as severe as it used to be a couple of years ago, but in quantum computing, I guess it's still not that common to find people who know about that. And then, especially if you think into the future where maybe smaller companies would like to solve use cases with quantum machine learning because they get some advantage out of it potentially, then of course the question is, how can we reduce these entry barriers? And luckily this problem has kind of been already solved, or at least tackled in the classical domain, where there's the concept of AutoML, which stands for automated machine learning. And the idea is basically you have sort of a black box. I mean, it doesn't need to be a black box. You can also customize it. But from a user perspective, the easiest thing is it could be a black box. You throw your data at it, and then the framework constructs a machine learning pipeline. So it pre-processes the data. It could be dimensionality reduction or scaling or anything. And then, of course, you have the problem of optimizing and selecting a suitable algorithm for a specific use case. And the output of this black box algorithm is in the end a model that, at least given a certain budget, will be optimal for your use case that you've specified. And the idea of the project, which is funded by BMWK and managed by the DLR Projektträger, is to just take this concept and integrate quantum machine learning. And that's the first pillar, where we want to throw into this algorithm pool. So do I have a laser pointer? No, right? Is that? Oh, sorry. No laser pointer. Okay. Where we want to throw in this optimization algorithm pool, just quantum machine learning algorithms. And for that, they, of course, have to be implemented in a way that they are highly customizable and also in a modular fashion. And the second pillar is we have this optimization and selection problem, which could also be, which is also an optimization problem, right? And then we ask the question, can this benefit from quantum computing as well? So can we use quantum computing to improve the methodology of AutoML itself? So these are the 2 basic principles. When I say we, then I mean we're a consortium of different partners. We have several industrial use case partners, KIB, ERV, Trumpf, and Zeppelin, who will speak to you later. And then we have software development partners with UNGFT and 2 Fraunhofer institutes, IAO and IPA, where I'm from. So, for today, I want to skip a little bit the second pillar and mainly concentrate on the first one. So how do we integrate the quantum machine learning into the AutoML? And when we started, we quickly found out that it is beneficial to just factor all this out into a separate framework, which is also open source now. So we've created a quantum machine learning library called sQUlearn, which has several high-level algorithms, but you can also tinker with it if you want to in the low levels. And it mainly provides several QNNs in different kinds of flavors, and also quantum kernel methods with fidelity kernels and projected kernels and several, I would say, convenience features. Okay. guess here an animation did not work as intended. Yeah, you can install it via pip if you want to try it. So, how does this look like in practice? So the idea was to implement this in a way that it can be used also as a standalone framework, independent from the automation, which will come on top, which I will talk about soon. And then the easiest thing was to just provide a scikit-learn interface, because the AutoML libraries that are out there, they can cope with a scikit-learn interface, and also everybody who's familiar with classical machine learning knows how to use that. And if you now look, for example, of how to train a quantum neural network, then you of course have a bunch of imports on top, which you usually have. Then you just define a circuit where we have a library of circuit, which also, of course, the framework needs to have a little bit of a choice. You define an observable, and then you're already good to go to create a quantum neural network. Where you see now, okay, maybe I don't have a pointer, but I can show you here. This is obviously running in a simulation, but it doesn't have to be. So we already also support several quantum computing providers, such as IBM, but also several computers that are available in AWS, for example, IonQ and I think Rigetti. And if you already set up your QNN, you just fit and predict like you would with any other or any other classical machine learning, and the rest is just handled under the hood. So if we go back to this initial picture, then we use sQUlearn to provide the algorithms in the algorithm pool. For optimization, we use a combination of RayTune and Optuna, where Optuna is basically there to just sample useful combinations, and then RayTune parallelizes it and optimizes the remaining degrees of freedom. sQUlearn also takes care of the quantum computing backends, which you can access via cloud. And we also have a session management, which is just a convenience feature. The framework itself is based on Qiskit and PennyLane, so both of these simulators are also usable. And for a given use case, maybe Qiskit is better for some reason, or you want to use the auto differentiation from PennyLane, then you can use that. And it's very flexible in that way. And so to sum it up, for now, we only support supervised quantum machine learning tasks, so classification and regression, but in several flavors. So we, for example, have time series classification and also like computer vision use cases that can work with the framework. And on the hardware, I already said, we support several hardware providers and also several simulation providers. And I think an interesting thing is that everything has been designed from the beginning with the hardware progress in mind. So we try to make it as modular and as extendable as possible. So as the hardware, for example, progresses, but also there could be algorithmic improvements, and then they could be integrated easily into the existing framework, as long as they provide just a scikit-learn interface. The framework is now in its final testing and will be available by the end of this year through GitHub and also through the platform Planck, if you're interested in that. And now I want to hand over to Horst, who will show you an application.
Okay, thank you, Marco. And before I come to the use case and the example, I briefly introduce Zeppelin, where I'm from. Zeppelin is a German company with locations in 26 different countries. We have more than 10,000 employees and a turnover in 2023 of around about 3.9 billion euros. Zeppelin, the Zeppelin holding is some kind of a roof with 5 different strategic business units located within it. There is the plant engineering for designing and constructing plants, whole plants or part of plants. There is power systems, which is a distributor for heavy combustion engines, for ships, for trains, or energy stations. Then we have rental. There you can rent everything that you need for construction sites. And then we have the two construction equipment units, international and Germany and Austria, and this is where the use case is located in. And the two construction equipment units are dealers for heavy construction machines, new and used construction machines. And our portfolio is really big, ranging from excavators, loaders, up to special solution equipments. So we are talking about hundreds of different models and thousands of different specifications. So especially for the colleagues of the used machine department, it is very hard and a real challenging task to assess all these different machines with the different specifications, and the assessment is needed when we buy these machines and when we try to sell these machines, because accurate and reliable prices, of course, are absolutely important to get a good profitability of all this. So what did we do? What is the solution? Of course, it's machine learning. And for that, we collected a huge mass of data, of current data from the internet, from different market portals like Mascos or mobile.de that sell, where you can sell and buy used construction machines. And we took this data, we cleaned the data, we prepared the data, and used it for our machine learning purposes. And we started to implement or to apply manual machine learning methods like random forest, support vector regression, or linear regression. And in addition, we added AutoML methods like AutoSQLearn and AutoGluon. And then we took a subset of this data set and also applied it to quantum machine learning methods. And why did we do all this? Because we just wanted to find out which is the best method for our use case and for our data. And especially for the quantum machine learning part, we just wanted to find out, okay, do we get any good results? Do we get results at all? Do we get good results? And how is this comparable to the classical machine learning methods, the automated and the manual one? And especially for the quantum machine learning part, we distilled this data set and came out with this data set that you can see here. That contains 141 data points. The distribution is depicted on the left side. The type of the data is, you can see in the middle, and at the bottom there is an excerpt of the data set with the extension, construction year, working hours, locations, and the price. And the price is our label, and that's exactly what we want to predict. That's what we are interested in. And with this data, we applied it to 4 QSVR methods, 3 of them with different fidelity quantum kernels and 1 with a projected quantum kernel. And we also applied this data set to a classical support vector regression method with an RBF kernel. And in addition, the data set is applied to AutoQML with 3 different methods that you can see here, QKRR, QSVR, and QGPR. They are placed within the search space of our AutoQML. And the framework that we used is depicted here. So after clearing the data set, removing outliers, etc., we got 2 different pillars. 1 manual pillar and 1 automated pillar. And within the manual pillar, we had to do autoencoding and scaling, and also dimensionality reduction for the use with the QML methods. And then we had to manually implement this 4 QML or QSVR methods and also the classical SVR method. So there's a lot of work that has to be done within this pillar, not just for the encoding stuff, for the preparation stuff, but also for implementing the different methods. On the other side, we have the AutoQML pillar, where we do not have to do this pre-processing steps, encoding, scaling, and dimensionality reduction. And also the application of AutoQML is really totally simple, just a couple of lines of code. I think as shown by Marco before, and everything is running. So there's a huge difference in labor that you had to do, and also in knowledge that you have to bring for these two different pillars. And we use MAPE, the mean absolute percentage error, as a score for our results. So just to evaluate how good they are and to compare them between each other. And the results are depicted here. And for me, it was a big surprise that AutoQML yielded the best result out of this. This was a run that took 10 minutes. And you can see smaller values are better, and it's slightly better than a manual implementation of a QSVR, but it is better. And on the right side, you can see the pipeline of the AutoQML, so the encoding stuff, the scaling, the dimensionality reduction, and at the bottom there is the method choice. And in this case, QKR gave us the best overall result, and that's why the AutoQML picked it. And there are some other informations, for example, the qubits needed. There are 4 qubits in this case that were needed for this results. Just to mention here, this is all simulated, so not yet implemented and run on a real hardware. I think this will follow up in the next weeks or hopefully months. So to sum up, we wanted to test and we demonstrated that AutoQML is potential to replace the manual implementation of QML methods with the result that you need much less labor to do and much less expertise to come to, I think, really good results. And with that, I want to end up. Thank you very much for your attention. If there are any questions, we will answer them.